Here with me is Ilya Sutskever. Ilya is co-founder and chief scientist of OpenAI. As a PhD student at Toronto, Ilya was one of the authors on the 2012 AlexNet paper that completely changed the field of AI, having pretty much everyone switch from traditional approaches to deep learning, resulting in the avalanche of AI breakthroughs we've seen the past 10 years. After the AlexNet breakthrough in computer vision, at Google, among many other breakthroughs, Ilya showed that neural networks are unexpectedly great at machine translation. At least at the time, that was unexpected. Now it's long become the norm to use neural nets for machine translation. Late 2015, Ilya left Google to co-found OpenAI, where he's chief scientist. Some of his breakthroughs there include GPT, Clib, DallE, and Codex, all of which I hope we'll be talking about. Any single of the 6 breakthroughs I just mentioned so far would make for an illustrious career, and Ilya has many more than those 6. In fact, Ilya's works, less than 10 years out of his PhD, are cited over 250,000 times, reflective of his absolutely mind-blowing influence on the field. Ilya, I have to say, I really miss our days together at OpenAI. Every day you were such a source of inspiration and creativity. So happy to have you here on the podcast. Welcome.
Thank you, Peter. Thank you for the introduction. I'm very happy to be on the podcast.
Well, I'm so glad we finally get to chat again. And we used to spend so much time together, and I'm really excited to kind of catch up on all the things you've been up to in the last few years. But first, I want to kind of step back a little bit to what is, I think many believe, definitely I believe, the defining moment of the modern AI era, which is the ImageNet breakthrough in 2012. It's the moment where a neural network beat all past approaches to computer vision by a very large margin. And of course, you were one of the people making that happen. And so I'm really curious, from your perspective, how did that come about? Everybody else is working on different approaches to computer vision, and there you are working on neural nets for computer vision, and then you drastically outperform everyone. How do you even decide to do this?
Yeah, I'd say that what led me to this result was a set of realizations over the time period of a number of years, which I'll describe to you. So I think the first really pivotal moment was when James Martins has written a paper called Deep Learning via Hessian-free optimization. And that was the first time anyone has shown that you can train deep networks end-to-end from supervised data. Mm-hmm. But for some context, back in those days, everybody knew that you cannot train deep networks. It cannot be done. Backpropagation is too weak. You need to do some kind of pre-training of some sort, and then maybe you'll get some kind of an oomph. But if it is the case that you can train them end-to-end, then what can they do? And the thing is, why? There is one more piece of context that's really important. So today we take deep learning for granted. Of course, a large neural network is what you need. And you shove data into it, and you'll get amazing result. Everyone knows that. Every child knows that. How can it be that we did not know that? How could such an obvious thing was not known? Well, people were really focused on machine learning models where they can prove that there is an algorithm which can perfectly train them. But whenever you put this condition on yourself and you're required to find a simple, elegant mathematical proof, you really end up restricting the power of your model. In contrast, neural networks, like the fundamental thing about neural networks is that they are basically little computers, little parallel computers that are no longer so little anymore. They definitely are, they can be as little or as large as you want, but basically it is a computer. It is a parallel computer. And when you train a neural network, you program this computer with a backpropagation algorithm. And so the thing that really clicked for me is when I saw these results with the Hessian-free optimized, I realized, wait a second, so we can actually program those things now. It's no longer the case that, maybe you could, so the prevailing view was aspirationally, maybe someone could train those things, but it's obviously impossible. Local minimas will get you.
Mm-hmm.
But no, you can train a neural net. Then the second realization is human vision is fast. It takes several hundred milliseconds at most to recognize something, and yet our neurons are slow. So that means that you don't even need that many layers to get respectable vision.
Mm-hmm.
So you put this. So what does that mean? It means that if you have a neural network which is pretty large, then there exist some parameters which achieve good results on vision. Now, if only there was a data set which we could train from, and then ImageNet came up, and then the GPUs came up, and then this has to happen. And then at some point, I had a conversation with AlexNet, where he said that he has GPU code which can train a small ConvNet to get respectable results on CFAR in 60 seconds. And I was like, oh my God. So let's do this on ImageNet. It's gonna crush everything. And that's how it happened. That's how it came to be.
I love the backstory here, Ilya, and how it reminds me a lot of our days at OpenAI, where many things to you just look unavoidable and just so clearly they have to be that way. I remember the first time you articulated to me that a neural net is just a computer program, and this is like several years before even Karpathy started talking about software 2.0 being, programming with neural nets, and it's just parallel and serial compute. It's really amazing that you saw this even before there was real success in neural nets. When did you realize it was actually working on ImageNet? What was that like?
I mean, I had very little doubt that it would work, but it was kind of, at this point, Alex was training the neural net, and the results were getting better week after week, and that's about it. But I felt like the big risk from my perspective was, do we have the ability to utilize the GPUs well enough? Train a big enough, big enough. There's no such thing. It's more like an interestingly large neural network. It has to be a neural network that is large enough to be interesting. Whereas all previous neural networks are small. If you're just going to have something which is going to be way larger than anything before, then it should do much better than anything anyone's ever seen. Of course, we are far beyond that. Our computers are faster and neural networks are larger. But the goal was just to go as far as possible with the hardware we had back then. That was the risk, and fortunately, Alex had the kernels that eliminated that risk.
Right, that's a very good point. I mean, at the time, it wasn't. I mean, today you put something in PyTorch, TensorFlow, whatever your favorite framework is, and you can train a neural network. Back then, you actually had to build some pretty specialized tools yourself to make this all run. Now, as that breakthrough happens, I'm curious, what are you thinking next? What do you think, like, okay, we do this. You probably knew this breakthrough happened before everybody else in the world, because, I mean, you had the results before the public workshop. And so before everybody else in the world even knew that neural nets are going to be the new state of the art and a new way of doing computer vision, you already knew that. And so where was your mind going at that point?
So I think there were two things which I was thinking about. So the belief, so my belief has been that we've proven that neural nets can solve problems that human beings can solve in a short amount of time. Because with the risk, we've proven that we can train neural nets with modest numbers of layers. And I thought we can make the neural networks wider, but and that will be pretty straightforward. Making them deeper is going to be harder. And so I thought, okay, well, depth is how you solve problems that require a lot of thinking. So can we find some other interesting problems that don't require a lot of thinking? And I actually was thinking a little bit about reinforcement learning, but the other problem was problems in language that people can understand quickly as well. So with language, you also have the property that you don't need to spend a lot of time thinking, what did they say exactly? Sometimes you do, but often you don't. So problems in language, and translation was the preeminent problem in language at the time. And so that's why I was wondering if we could do something there. Another thing which I was thinking about was actually Go as well. I was thinking that using a ConvNet could potentially provide very good intuition for the non-neural network Go plane system that existed back then.
Can you say a bit more about the Go system? how a neural network could and actually has changed then from there, how that's done?
I mean, basically, the thing about neural networks is that, okay, so before deep learning, anything you had to do with AI involved some kind of maybe search procedure with some kind of hard-coded heuristics where you have really experienced engineers spend a lot of time thinking really hard about how exactly, under what conditions they should continue something or discontinue something or expand resources. And they just spent all their time trying to figure out those heuristics. But a neural network is formalized intuition. It is actually intuition. It gives you the kind of expert gut feel. Because I read this thing that an expert player in any game can just look at the situation and instantly get a really strong gut feel. It's either this or that. And then they spend all their time thinking which of those two it is. You say, great, the neural network should have absolutely no trouble if you buy the theory that we can replicate functions that humans can do in a short amount of time, like less than a second. And it felt like, okay, in case of something like Go, which was a big unsolved problem back then, a neural net should be able to do that.
Back in the time, Ilya, well, the first time I heard that, maybe use a ConvNet for Go, my naive reaction, obviously, because clearly it succeeded. My naive reaction was, ConvNets are famous for translation invariance. And there's no way that we want to be translation invariant on the board of Go, because it really matters whether a pattern is in one place or another place. But obviously, that didn't stop the ConvNets from succeeding and just capturing the patterns nevertheless.
Yeah, I mean, that's again the power of the parallel computer. Can you imagine programming a ConvNet to do the right thing? Well, it's a little bit hard to imagine that, but it's true that part may have been a small leap of faith. And maybe to close the loop on Go. So my interest in Go ended up in me participating on the AlphaGo paper as well, in a modest way. Like I had an intern, Chris Madison, and we wanted to apply ConvNets to Go. And at the same time, Google acquired DeepMind, and all the DeepMind folks have visited Google. And so we spoke with David Silver and Ajay Huang, and we thought it'd be a cool project to try out. But then DeepMind, really, they put a lot of effort behind it, and they really had a fantastic execution on this project.
Yeah, I think while the ImageNet moment is the moment most AI researchers saw the coming of age of deep learning and a whole new era starting, AlphaGo is probably the moment most of the world saw that AI is now capable of something very different from what was possible before. It's interesting, though, because while most of the world's focused on that, around the same time, actually, a New York Times article comes out saying that actually something very fundamental has been happening in natural language processing, which you alluded to, and that actually the whole Google Translate system had been revamped with neural networks. Even though a lot of people think of neural nets at the time as pattern recognition, and patterns should be signals like speech or visual signals, and language is discrete. And so I'm really curious about that. How do you make the leap from these continuous signals where neural nets, to many people, seem the natural fit, to language, which most people would look at as discrete symbols and very different?
Yeah, so I think that leap is very natural if you believe relatively strongly that biological neurons and artificial neurons are not that different. Because then you can say, okay, human beings, let's think of the single best professional translator in the world, someone who is extremely fluent in both languages. That person could probably translate language almost instantly. So there exists some neural network with a relatively small number of layers in that person's mind that can do this task. Okay, so if you have a neural network inside our computer, which might be a little bit smaller, and it's trained on a lot of input-output examples, we already know that we will succeed in finding the neural net that will solve the problem. So therefore, the existence of that single really good instantaneous translator, or the existence of one such person is proof that a neural network can do it. Now, it's a large neural network. Our brains are quite large. But maybe you can take a leap of faith and say, well, maybe our digital neurons, we can train them a little bit more, and maybe they're a little bit less noisy, and maybe it will still work out. Now, of course, our neural networks are still not at the level of a really amazing human translator, so there's a gap. But that was the chain of reasoning, that humans can do it quickly. Biological neurons are not unlike artificial neurons. So why can't a neural network do it? Let's find out.
With your collaborators at Google, you invented the modern way of doing machine translation with neural networks, which is really amazing. Can you say a little bit more about how that works?
All you need is a large neural network with some way of ingesting some representations of words. And when a representation of words, so what does it mean, a representation? It's a word that we use in AI often. A representation is basically, okay, so you have the letter A. How do you show it, or the word cat? How do you present it to the computer, to the neural network? Mm-hmm. And you basically just need to agree with yourself that, hey, we're going to create some kind of a mapping between the words or the letters into some kind of signals that happen to be in the format that the neural net can accept. Mm-hmm. So you have this, you just say, I'll just design this dictionary once and feed those signals to the neural net. And now you need to have some way for the neural network to ingest those signals one at a time. And then it emits the words one at a time of the translation. Mm-hmm. And that's literally it. It's called the autoregressive modeling approach, and it's quite popular right now. But it's not because it's necessarily special. It's just convenient. The neural networks do all the work. The neural networks figure out how to build up their inner machinery, how to build up their neurons so that they will correctly interpret the words as they come in one at a time. And then somehow, break them into little pieces and transform them, and then do exactly the right orchestrated dance to output the correct words one at a time. It's probably possible to design other neural networks that are other ways of ingesting the words, and people are exploring this right now. You may have seen some, if you follow ML Twitter, you may have seen some words like phrases like diffusion models. Mm-hmm. So maybe they will be able to ingest the words in parallel and then do some sequential work and then output them in parallel. It doesn't actually matter. What matters is that you just present the words to the neural net somehow, and you have some way that the neural net can output the words of the target. And that's what matters.
Yeah, to me, it was a very big surprise at the time that it worked so well for language. I was 100% set on that it will work great for anything continuous. And then all of a sudden, the sequence-to-sequence models that you pioneered was like, okay, well, I guess now it's going to work for everything, was my conclusion. Because if it can work for language, what's left in terms of signals we work with, right? Now, you, of course, didn't start working on neural nets from the day you're born. And Ilya, I'm really curious, where did you grow up, and how did that lead you to ending up, being an AI researcher?
Yeah. So I was born in Russia. I grew up in Israel, and then I moved to Canada when I was 16. According to my parents, I've been talking about AI at a relatively early age. And I definitely remember at some point thinking about AI and reading about this whole business with playing chess using brute force. And it was totally clear. It seemed that, yeah, you could do the chess stuff, no problem. But the learning stuff, that's where the real meat of AI is. That's why AI is so terrible, because it doesn't learn, and humans learn all the time. So can we do any learning at all? So when my family moved to Canada, to Toronto, and I entered the University of Toronto, I sought out the learning professors, and that's how I found Jeff Hinton. And then the other thing is that he was into training neural networks, and neural networks seemed like a much more promising direction than the other approaches, because they didn't have obvious computational limitations, like things like decision trees, which were that phrase was popular back in the day.
Mm-hmm. Now, Jeff, of course, has a very long history working in AI, and especially neural networks, deep learning. Coming out of England, coming to the US, then moving to Canada, and his move to Canada in some sense helped spark the AI, the beginning of the new AI era in Canada, of all places, right? You're there at the same time, which is really interesting. Kind of curious, do you think there's any reason your parents decided to go to Toronto, and that it is like the place where both you and Jeff ended up, and Alex, I mean, the three of you were there together to make that happen?
I think it's a bit of a happy coincidence. I think it has to do with the way immigration works. It is a fact that it is quite a bit easier to immigrate into Canada. And if you immigrate into Canada, Toronto is perhaps the most appealing city to settle in.
Now, that coincidence brings you to University of Toronto, and you find Jeff Hinton working on neural networks. But I got to imagine when you looked into his history, you must have noticed he'd been working on it for 30, 40 years. And was there any moment you thought, well, maybe if it doesn't work after 30, 40 years, it's not going to work now either?
I see what you're saying, but my motivation was different. I had a very explicit motivation to make even a very, very small but a meaningful contribution to AI, to learning. Because I thought learning doesn't work at all completely. And if it works just a little bit better because I was there, I would declare it a success. And so that was my goal.
And do you remember anything from your first meetings with Jeff? How was that?
I mean, so I was a third year undergrad when I met him for the first time. I mean, I thought it was great. So my major in undergrad was math. But the thing about math is that math is very hard. And all the really talented people would go into math. And so one of the things which I thought was great about machine learning is that not only it is the thing, but also all the really clever people go into math and physics. So I was very pleased about that.
What I remember from actually reading Cade Metz's book is actually possibly my favorite anecdote from the book. Has Jeff telling the story about him meeting you, Ilya. And so here's how the book tells the story. Maybe you've read it, maybe not, but essentially the book says, yeah, there's Jeff, and this young student comes in, Ilya Sutskever, undergrad still, and Jeff gives you a paper. And you go read it, and you come back and you tell him, I don't understand it. And Jeff's like, oh, that's okay. You're still undergrad. What don't you understand? I can explain it to you. And essentially you say, actually, I don't understand why why they don't automate the whole process of learning. It's still too much hand holding. I understand the paper. I just don't understand why they're doing it that way. And Jeff's like, okay, wow, this is interesting. It gives you another paper. And again, you go read, you come back, so goes the story, and you say, oh, I don't understand this one either. And Jeff's like, what do you understand? Don't you understand about this one? I'm happy to explain. And you go, I don't understand why they train a separate neural network for every application. Why can't we train one gigantic network for everything? It should help to be trained jointly. And to me, that's really, that reminds me a lot of our times at OpenAI, where it always felt like you are, already thinking, several steps into the future of how things are going to shape up, just from the evidence we have today, how it really should be several years down the line. That, at least according to the book, that's how Jeff remembers the first two meetings with you.
Yeah, something like this did happen. It's true. So the field of AI back then, when I was starting out, was not a hopeful field. It was a field of desolation and despair. No one was making any progress at all. And it was not clear if progress was even possible. And so that's why, what do you do when you are in this situation? So you say, you're walking down this path. This is the path, the most important path, but you have no idea how long it is. You have no idea how hard it's going to be. What would be a reasonable goal in this case? Well, the goal which I chose was, can I make a useful step, one useful step? So that was my explicit motivation, at least for quite a while, before it became clear that actually the path is going to become a lot sloppier and a lot more rapid where ambitions grew very rapidly. But at first, when there was no gradient, the goal was just make any step at all, anything useful that would be meaningful progress towards AI.
And I think that's really intriguing, actually, Ilya, because I think that's what drives a lot of researchers is to just find a way to make some progress, not knowing actually ahead of time how far you can get, but just being so excited about the topic that you just want to find a way to at least make some progress and then keep going. And it's of course very interesting in your case that then the whole thing switched from slow progress to ever faster progress all of a sudden, thanks to the thing that you're like, look, you're trying to make that bit of progress, and it turns out to open up the floodgates for massive progress. Now you start in Canada. Your PhD research, of course, completely changes the field. You start a company that gets acquired by Google, and you're at Google. But then the big thing, and also the moment actually our paths start crossing or about to cross, is that you're on this role at Google. You're doing some of the most amazing pioneering work in AI. You're clearly in an amazing situation where you are, doing some of the best work that's happening in the world, and you decide to change your situation. How did that come about?
I remember being at Google and feeling really comfortable and also really restless. I think two factors contributed to that. One is that I somehow could look 10 years into the future, and I had a little bit too much clarity about how things will look like. And I didn't enjoy that very much. But there was another thing as well, and that's the experience of seeing DeepMind work on AlphaGo. And it was very inspiring. And I thought that it's a sign of things to come, that the field is starting to mature. Up until that point, all progress in AI has been driven by individual researchers working on small projects, maybe small groups of researchers with some advice by their professors and maybe some other collaborators. But usually it would be small groups. Most of the work would be idea heavy, and then it would be some kind of some effort on the engineering execution to prove that the idea is valid. But I felt that AlphaGo was a little different. It showed that, in fact, it showed to me that the engineering is critical. And in fact, the field will change and will become the engineering field that it is today. Because the tools were getting very solid. And the question then becomes, okay, how do you really train those networks? How do you debug them? How do you set up the distributed training? And it's a lot of work, and the stack is quite deep. And I felt that the culture at Google was very similar to the academia culture, which is really good for generating radical novel ideas. And in fact, Google has generated a lot of radical and revolutionary ideas in AI over the years, and most notably the transformer from the past few years. But I felt that that's not going to be the whole of progress in AI. I felt that it's not now only a part of progress in AI. So if you think of it as of the body, you can say you need both the muscles and the skeleton and the nervous system. And if you only have one, it's amazing, but the whole thing won't really move. You need all the things together. And so I felt that I had a vague feeling that it would be really nice if there was some kind of a company which would have these elements together. But I didn't know how to do it. I didn't have any path to it. I was kind of just daydreaming about it. And then at some point I got an email from Sam Altman saying, hey, let's get dinner with some cool people. And I said, sure. And I showed up, and Greg Brockman was there, and Elon Musk was there, and a few others. And we just chatted about, wouldn't it be nice to start a new AI lab? And I found that really the time was right, because I was thinking about the same thoughts independently. And I really wanted it to be engineering heavy. And now seeing that Elon was going to be involved, I thought, well, who better to learn? Who would be better? Can't imagine a better person from whom to learn the big engineering project side of things. So I think this was the genesis. There is there is more to it, but I think that was the real genesis of OpenAI from my perspective. That I was thinking about something, and then just one day I woke up with this email. Hey, the thing that from my perspective was like I was daydreaming about something, and then my daydream came true, almost like this.
The daydream becomes true. What you're really saying there is that there is a group of people, very highly accomplished and ambitious people, who are in some sense aligned with your dream and want to make this happen together. But all that gets you is essentially, some paperwork that a new company now exists, and maybe some money to get going. But you actually still need to decide what to do with those resources and with your time. I'm kind of curious, at the beginning of OpenAI, what was going on in your mind in terms of how to shape this up? Obviously it's been a massive success, but I'm really curious about that the beginning part and how that played out for you.
So the beginning part, I would describe it as a whole lot of stress. And it wasn't exactly clear how to get going right away. There was only clarity about a few things, which is there need to be some kind of a large project. And I also was excited about the idea that maybe if you can predict really well, you would make progress on unsupervised learning. But beyond that, it wasn't clear what to do. So we tried a whole lot of different things. And then we decided that maybe it would be good to solve a difficult computer game, Dota. And if this is where Greg just showed his strength, and he just took on this project, even though it seemed really impossible, like genuinely impossible, and just went for it. And somehow it worked in the most stereotypical deep learning way, where the simplest method that we tried just ended up working. The simplest policy gradient method, as we kept scaling it up. It just never stopped improving with more scale and more training.
Just to double click on that for a moment, I don't think everybody knows what Dota is. Can you say a bit about that? I fully agree. Why it's so surprising that the simplest approach ultimately works is a very hard problem.
So for some context, the state of the field back then was, okay, so if you look at reinforcement learning in particular, DeepMind has made some very exciting progress. First, by training a neural net with reinforcement learning to play simple computer games. And then the reaction was, okay, that's exciting and interesting and kind of cool, but what else can it do? And then AlphaGo happened. And then the opinion has shifted. Okay, reinforcement learning maybe can do some things, but Go, it's funny, by the way, Go used to look to be this impossible game. And now everyone says, oh, it's such a simple game. The board is so small. Our perceptions change quickly. But then DeepMind were talking about how StarCraft is the next logical step after Go. And it made a lot of sense to me as well. It seemed like a much harder game, not necessarily if a person were to play it, but for our tools, it seemed harder because it had much more. You had a lot more moving parts. It's much more chaotic. It's a real-time strategy game. And we thought that it would be nice to have our own twist on it and to try to make a bot which can play Dota. And Dota is another real-time strategy game that's really popular. I believe it definitely had, I don't know if it still has, the largest annual prize pool of any professional esport game. Wow. So it has a very vibrant, very strong professional scene. People dedicate their lives to playing this game. It's a game of reflex and strategy and instinct, and a lot of things happen. You don't get to see the whole game. The point is that it definitely felt like a grand challenge for reinforcement learning at that time. And our opinion about the tools of reinforcement learning was, so let's put it this way. So the grand challenge felt like it's here. And the field's opinion about the tools and their ability to solve a problem like this was like here. There was a huge mismatch. And so when we started working on it, we thought, oh yeah, we're going to need to develop all kinds of crazy planning methods and hierarchical reinforcement learning methods and whatnot. But let's just get a baseline. Let's just see when the baseline breaks. And that's when the baseline just didn't break. It just kind of kept improving all the time. And it's interesting with each, so what would happen over the course of this project, we would have these public demonstrations of our progress. As we'd reach different milestones of performance, we would have some kind of a public exhibition game against a professional of different level of accomplishment. So at first we had a public exhibition game against retired professionals. Then we had them against active professionals. And then finally we had a game against the strongest professionals and we defeated them. Mm-hmm. But the interesting thing is that at each step, you'd have very knowledgeable experts in ML who would come out on Twitter and say, well, that was really cool, great successful reinforcement learning, but obviously the next step would require the explicit planning thing or the hierarchy thing. Mm-hmm. And somehow it did not. So that was a very important result for us. I felt like it really proved to us that we can do large projects.
I remember I was not part of this project, just to be clear, but I was there at OpenAI when it was all happening, working on other projects, and I remember being very, very surprised, that no explicit structure was needed. Though, well, in my mind, obviously, but maybe it's not even true. But in my mind, there is this large LSTM model neural network that maybe somehow through backpropagation actually internalized the structure that we all, at least not all of us, but maybe me, I thought we would have to put in explicitly. And maybe the neural network was able to just absorb that intuition through backpropagation without the need to hard code it, which was really intriguing to me because it just seemed like, wow, a lot of intuitions might be better provided through data than through hard coding, which seems a very common trend in all of deep learning. But maybe in reinforcement learning at the time wasn't as strongly believed yet till that result came out.
Yeah, I mean, I agree. I agree with your assessment. I feel like, yeah, I like to think that this result had changed the field's view at least a little bit about the capability of simple reinforcement learning. Now, to be fair, you still need quite a hefty amount of experience to get a very strong result on such a game. And then we also used a similar approach. So I would say, if you have the ability to generate a very large amount of experience against some kind of a simulator, then this style of reinforcement learning can be extremely successful. And in fact, we have also another important result in OpenAI's history was to use the same exact approach to train a robot to solve the Rubik's Cube. So a physical robot hand, actually solved the physical Rubik's Cube. And it was a quite challenging project. The training was done entirely in simulation. And the simulation was designed in such a way so that it's extra hard and it requires the neural net to be very adaptive so that when you give it the real robot, the real physical robot, it will still succeed. But at core, it was the same exact approach as the one we used with the DOTA project, which was very large scale reinforcement learning. In fact, it was even the same code. So that was a case where we had this general technique, these general powerful results, which we were able to use in more than one place. And that was what we've done on reinforcement learning.
Now, I know that right now there's other reinforcement learning happening at OpenAI in the context of language, actually. Before we get to, and I'm really curious about that, but before we get to that, language modeling, GPT, is probably the most visible thing in recent years in the public eye of what AI is capable of. And OpenAI generated these GPT generations of models that can complete articles in very credible ways, and it's been very surprising how capable It is. And so what I'm really curious about, again, in some senses, you decided that, or I mean, not alone, but together with collaborators at OpenAI, you decided that, it was time was right to go down this path of, building language models. And I'm really curious, what was it for you that made you believe that, this was the thing to start doing?
Yeah. So from my side, a really important thing that happened to me is that I was really interested in unsupervised learning. And for context, the results that we spoke about earlier on, about vision and even about, Go and Dota, all these results, translation, they are all cases where you have somehow, you train a neural network by presenting it with inputs and desired outputs. You have your random input, not random. You have a typical input, a sentence, an image, something, and you have the desired output. And the neural network, you run it, and you compare the predicted output with the desired output. And then you change the neural network to reduce this error. And you just do it a lot. You do it a lot, and that's how learning works. And it's completely intuitive that if you will do this, the neural network will succeed. I should say, maybe not completely intuitive, but definitely pretty intuitive today. Because you say, hey, here is my input, here's my desired output, don't make the mistakes. Eventually, the mistakes will go away. And it is something where you can at least have a reasonably strong intuition about why it should work, why supervised learning works, and why reinforcement learning works. In contrast, at least in my mind, unsupervised learning is much more mysterious. Now, what is unsupervised learning exactly? It's the idea that you can understand the world, whatever that means. You can understand the world by simply observing it, without there being a teacher that will tell you what the desired behavior should be. So there is a pretty obvious question, which is, okay, so how could that possibly work? How could it possibly be that you have, okay, so what would you do then? What was the typical prevailing thinking? The prevailing thinking has been that maybe you have some kind of task like you take your input, your observation, an image, let's say, and then you ask the neural network to somehow transform it in some way and then to reproduce the same image back. But why would that be a good thing for the task you care about? Is there some mathematical reason for it? I found it very unsatisfying. In my mind, it felt to me like there is no good mathematical basis for unsupervised learning at all whatsoever. And I was really bothered by it. And after a lot of thinking, I developed the belief that actually, if you predict the next bit really well, you should have a really good unsupervised learning. The idea is that if you can predict the next bit really well, then you have extracted all the meaningful information, that somehow the model knows about all the meaningful information that exists in the signal. And therefore, it should have a representation of all the concepts. And it's the idea in the context of language modeling, it's very intuitive. If you can predict the next word moderately accurately, maybe the model will know that words are just clusters of characters separated by space. If you predict better, you might know that there is a vocabulary, but you won't be good at syntax. If you improve your prediction even further, you'll get better at the syntax as well, and suddenly you will be producing syntactical mambo jumbo. But if you improve your prediction even further, necessarily the semantics has to start kicking in. I felt that the same argument can be made about predicting pixels as well. So at some point, I started to believe that maybe doing a really good job on prediction will give us unsupervised learning, which back then felt like a grand challenge. Another interesting thing that now everyone knows that unsupervised learning just works. But not that long ago, it seemed like this completely intractable thing. So anyway, to come back to the story of how the GPTs were created. So then, I'd say the first project that really was a step in this direction was led by Alec Radford, who is an important hero of the GPT saga, where we trained an LSTM to predict the next character on reviews, on Amazon reviews of products. And we discovered that this LSTM has a neuron which corresponds to sentiment. In other words, if you're reading a review which is positive, the sentiment neuron will fire. And if you're reading a review which is negative, the sentiment neuron will not fire. So that's interesting. And that felt to us like it validated the conjecture of, yeah, of course, eventually, if you want to predict what comes next really well, you need to discover the truth about the data. And so then what happened is that the transformer came out. And then we saw the transformer, and I think it was pretty, like, it got us really excited because we were really struggling. We believed that long-term dependencies were really important. And the transformer had a very clean, elegant, and compute-efficient answer to long-term dependency. And for context, the transformer is this neural network architecture. And in some sense, it's just really good. But a little bit more technically, so we discussed that these neural networks are deep in some way. And we know, and it's been the case until relatively recently, that it was pretty hard to train deep neural networks. And previous neural networks for training models on sequences of language, the longer the sequence was, the deeper the network would get, the harder it would be to train. But the transformer decoupled the depth of the transformer from the length of the sequence. So you could have a transformer of manageable depth with very long sequences. And that was exciting. And this investigation led to GPT-1. And then I would say further, then we continued to believe in scale, and that led to GPT-2 and 3. And here it's really, I wanna call out Dario Amodei, who really believed that if we were to scale up the GPTs, it will be the most amazing thing ever. And that's how we got GPT-3.
And GPT-3, I mean, when it came out, it wasn't just, I think what was so exciting to the entire community, it wasn't just something that could complete text. When you start with a prompt, it could maybe say, oh, this is likely your next sentence. It could complete all kinds of things. People would write web pages, even write some very basic code that gets completed with GPT-3. They would, and they would be able to prompt it. And that really intrigued me, this notion of prompting, where you have this gigantic model that's trained on, I don't know how much text out there, but that somehow when you then briefly feed it a little bit of extra text in the moment, you can actually prime it to start doing something that you want it to do. Can you say a bit more about that? Where did that come from, and how does that work, you think?
So what is a language model exactly?
Mm-hmm.
You just have a neural network that takes some text and tries to output an educated guess of what the next word might be. And it outputs an educated guess. It might say, it's 30% the word the, some kind of a guess of probabilities of what the words might be. Then you can pick a word according to this probability that the neural network outputs, and then commit to it, and then ask the neural network to predict the next word again and again and again. Now, we know that real text, in some sense, is very responsive to its beginning. Like, we know that text has a lot of very complicated structure. And if you read a document which says, this document below will describe a list of questions that were given in the MIT entrance exam in the 1900s, I just made it up, then I strongly expect that, in fact, there will be 10 or so questions in math of the kind of math that was usually in math exams in the 1900s. If the model is good enough, it should actually do that. Now, how good enough is good enough? Well, this is a little bit of a qualitative statement. But if it is definitely good enough, it should be able to do it. So then you train a GPT-3 and you see, can it actually do it? And sometimes it cannot, but very often, indeed, it is responsive. It is very responsive to whatever text you give it. Because to predict what comes next, correct well enough, you need to really understand the text you're given. And I think this is kind of, in some way, the centrality of prediction. Good enough prediction gives you everything you could ever dream about.
We are dropping new interviews every week, so subscribe to The Robot Brains on whichever platform you listen to your podcasts. Now, one of the things that I think also stood out to me with GPT is that it's a research breakthrough. It's a major research breakthrough, but it also feels very practical. Like, I mean, whenever I'm typing something, I mean, I know what I want to type next. It's already in my head, but I still have to type it. But with a GPT, GPT-2 onwards, probably, it could complete it fairly accurately. And so it seemed like very different in that sense from, for example, the Rubik's Cube breakthrough or the Dota breakthroughs, which were fundamental research breakthroughs, but it was hard to dream of the direct applications. And here with GPT, it was so easy to dream of so many applications. And I'm curious if that, in your own kind of evolution on things, when GPT started working, did you start thinking about applications, or did, more generally, if people around you at OpenAI start thinking about applications? What was going on?
Yeah, we were definitely excited about the potential applications. I mean, we were so excited about them that we built a whole API product around GPT-3 so that people could go and build their new and convenient and sometimes unprecedented applications in language. I mean, I think it's a general. So maybe another a way of looking at what's happening is that AI is just continuing to get more and more capable. And it can sometimes be tricky to tell if a particular research advance is real or not real. Suppose you have some cool demo of something. Like, what do you make of it? It can be hard to understand the magnitude of the advance, especially if you don't know how similar the demo is to their training data, for example. Mm-hmm. But if you have a product that's useful, then the advance is real. And I feel that maybe in a sense, we have moved away from, the field has matured so much that we no longer need to rely on demos and even benchmarks as the only indicators of progress, but usefulness as the truest indicator of progress. And so that's why I think this is a good sign for GPT-3 for sure. And yeah, the applications, we were excited about them, and people are using GPT-3 all the time right now.
Are there any uses that you've seen that you're able to share, the applications being built?
There's plenty of applications. I remember seeing something that helps you write a resume and prettify it. Something that helps improve your emails. I think I've seen something like this. I don't remember, but they all have this kind of flavor. I know that there is a lot of users. Unfortunately, I don't remember specific examples off the top of my head.
This is jumping ahead a little bit in the progression of the research trajectory you've gone through with OpenAI, but maybe the biggest application, of course, and maybe it's not called GPT anymore, it's called Codex, but it's very similar. It's a system that can help you write programs. Can you say a bit about that, and how is it? I'm curious. Is it just like GPT but trained on GitHub code instead of text, or are there some differences?
So the system that we describe in the paper is essentially a GPT trained on code. It's that simple. The thing that's interesting about it is that it works as well as it does. Because you can say, like, what have you even done? You've done nothing. You just took a large neural net and you trained it on code from GitHub. But the result is not bad at all. Its ability it can solve real coding problems much better than I think most people would have expected. And again, this comes back to the power of deep learning, the power of these neural nets. They don't care what problem to solve. And you can all kind of say, well, people can code, so why can't neural nets? If you believe that a biological neuron is not very different from an artificial one, then it's not an unreasonable belief at all. So then the question becomes, what's the training data? Mm-hmm. Predicting GitHub is not exactly the same as coding. So maybe it won't quite do the right thing. But it turned out to be good enough. And it turned out to be very useful, especially in situations where you have a library which you don't know. Because it's right all of GitHub, it has such familiarity with all the major libraries. And if you don't know it, but you kind of just write a comment, use this library to do X, it will come up with code which is going to often be correct or pretty close. And then you have something to work with, and you edit it a little bit, and you have something working. But yeah, it's just the GPT trained to predict code pretty well.
I think in many ways it's really mind-blowing in terms of potential societal impact, because if I think about a lot of the way we create impact in the world as people, we're often sitting behind a computer, right? And we're typing things. And whether it's typing emails or writing up documents on work we've been doing or writing code, this could really accelerate anybody's work and the kind of things we could do in one day. I don't know if we're already seeing metrics for this, but I would imagine that, if it's not now, in the next generation. And I'm curious about your thinking, what kind of productivity we can expect from people thanks to these tools.
So I'd say that in the near term, productivity will continue to increase gradually. I think that as time goes by and the capability of AI systems increases, productivity will increase absolutely dramatically. I feel very confident in that. We will witness dramatic increases in productivity. Eventually, in the long term, a day will come when the systems will, in fact, the world will be kind of like the AI is doing all the work, and then that work is given to people to enjoy. That's what I think is the long-term future will hopefully be like. So in the medium term, it's going to be amazing productivity increases. And then in the long-term future, it's going to be like infinite productivity or fully automated productivity.
Now, one of the things that, of course, people think about a lot in that context, when you're given AI a lot of productivity, it better be productive doing the right thing, and it better not be productive, I don't know, blowing something up by mistake and so forth, or just misunderstanding what it's supposed to be doing. And in that sense, I've been really curious about this project at OpenAI where reinforcement learning is combined with GPT. Can you say a bit more about that?
Take a step back. So we have these AI systems that are becoming more and more powerful. And a great deal of their power is coming from us training them on very large data sets we don't understand, for which we have an intuitive understanding of what they do. So they learn all kinds of things. And then they act in ways which we can inspect, but perhaps not. We can inspect, but it might be, and we do have, for these large language models, for example, we do have some ability to control them through the prompts. And in fact, the better the language model will get, the more controllable it will become through the prompt. But we want more. We want our models to do exactly what we want, or act closer to what we want as much as possible. So we had this project, indeed, that you alluded to, of training these language models with reinforcement learning from human feedback, where now you do reinforcement learning not against a simulator, but against human judges that tell you whether the output was desirable or undesirable. And if you think about it, this reinforcement learning environment is really exciting. You could even argue that reinforcement learning has kind of maybe slowed down a little bit because there weren't really cool environments in which you could do it. But doing reinforcement learning with language models and with people, that feels like it opens such a powerful vista. You can do so many things there. And what we've shown is that these large neural networks, these large GPT models, when you do reinforcement learning from these teachers, essentially. And I should also say there is a small technicality, which again, this is a technical thing for the ML-focused subset of the audience. In reinforcement learning, you're usually providing a reward, good or bad. But the way we do it with reinforcement learning from human feedback is that the teacher needs to look at two outputs by the model and to say which one is better, because it's an easier task. It's an easier task to compare two things than to say whether one thing is good or bad in absolute. And then we do a little bit of machine learning in order to then create a reward out of it, a reward model, and then use this reward model to train the neural net. And this is a pretty sample efficient thing to do. And you obtain a very fine-grained way of controlling the behavior of these neural networks, of these language models. And we've been using it quite a bit. Like recently we've been training these instruction following models, which actually people can use through the API, through the OpenAI API, where in GPT-3, the model is just trained on the internet. So you need to be quite clever about specifying your prompt into kind of core and getting the model to do what you want, providing it some examples. Whereas the instruction following model has been trained in this way to literally do what we tell it to. So there's a word which I think is known in some subsets of the machine learning community, but not in all of it. And it's called, the model this is an attempt to align the model. So that the model, with its power and with great power and unclear capabilities, will in fact be trained and incentivized to literally do what you want. And with the instruction following model, you just tell it what you want. Do X, write Y, modify Z, and it will do it. So it's really convenient to use. And this is an example of the technique of reinforcement learning from human feedback in practice. But moving forward, of course, you want to learn from teachers in all kinds of ways. And you want to use machine learning to not just have people, provide supervised examples or provide rewards, but you really want to have a conversation where you ask exactly the right question to learn the information that you need to understand the concept. So that's how things will be in the future. But right now, this approach has been used fairly successfully to make our GPT models more aligned than they are naturally.
I'm going to say aligned. As I understand it, you can also align them in a personalized way. So align to a specific person's preferences. Like I could teach it to follow my preferences and you could have a different one.
I mean, so the answer is definitely yes. So the specific model that I mentioned to you, the instruction following model, this model, it's a single model and it's been aligned. We say it's aligned, which is a way to say that it's been trained and incentivized to follow the instruction you give it. So it's an interface, and it's a very convenient interface. Of course, it is possible with these neural nets, they can do whatever you want. You can train them in literally any way you want. You can personalize them in arbitrary ways. You could say, okay, for this user, you do this, for that user, you do that. And the user can be specified with the paragraph or maybe with some of their past actions. So almost anything is possible.
Now, when you say almost anything is possible, that also reminds me of a lot of our past conversations. It always seems like, no limits to your imagination of what might be possible and angles to try to get there. And maybe one of the other most surprising recent results is, traditionally a lot of work in computer vision, in language processing, in reinforcement learning, kind of separate research arenas almost. But then recently, you, together with collaborators at OpenAI, released the CLIP and DallE models that bring language and vision, in some sense, together into the same network to really somehow have a single network that can handle both at the same time. I'm I'm curious about, how did you come to conclude, okay, this is the direction that maybe we should push now. Maybe it becomes possible now to have this combined model that can handle both vision and language in the same model and effectively translate between them as desired.
Well, I think the underlying motivation here is that it seems implausible that the neural networks of the future will not have both vision and language. And that was the motivation to begin thinking in this direction. And as to whether this should be possible, I think, at least in my view, there was plenty of evidence that neural networks should just succeed at this task. If you make it large and you have an appropriate data set. If they can generate language like they do, why can't they generate the language of images? Or go in the other direction as well. So it was more, maybe it's good to think of it as an exploration of training neural networks on both images and text. And with DallE, for context, DallE is literally a GPT-3 that is trained on text followed by almost like a textual representation of an image. So we use those tokens to represent an image, so that from the perspective of the model, it's just some kind of a funky language. But it's kind of like, you can train GPT on English text, on French text. It doesn't care. So what if you just had a different language, which had some human language and the language of images? And that's DallE. And it worked exactly as you'd expect. And it was still a lot of fun to see a neural network generate images like it did. And with Clip, it was an exploration in the opposite direction, which is, can a neural network learn to see using a lot of loose natural language supervision? Can it learn a huge variety of visual concepts? And can it do so in a way that's very robust? So that, and I think the robustness point is something which I think is, it's also very flexible, but I think the robustness point is especially important in my eyes, and let me explain what I mean by robustness. So there is one thing which I think is especially notable and unsatisfying in neural networks for vision, is that they make these mistakes that a human being would never make. So we spoke earlier about the ImageNet dataset and about training neural networks to recognize the images in this dataset. And you'd have neural nets which achieve superhuman performance in this dataset. Then you put it on your phone and start taking photos, and you could make all these disappointing mistakes. What's going on? And then it turns out that what's really going on is that there are all kinds of peculiarities to this data set which are hard to notice if you don't pay close attention. And so people have built all kinds of test sets with the same objects, but from maybe unusual angles or in a different presentation, for which the ImageNet neural network just failed. But the Clip neural network, it was trained on this vast and loosely labeled data from the internet with text. This neural network was able to do well on all these variants of ImageNet. It was much more robust to the presentation of the visual concept. And I think this kind of robustness is very important because human beings are in when it comes to our vision, a third of our brain is dedicated to vision. Our vision is unbelievably good. And I feel like this is a step towards making neural nets a little bit more robust, a little bit more neural nets whose capability is a little bit more in line with the capability of our own vision.
Now, you say ImageNet versus the Clip dataset. The Clip dataset is a lot larger. How much larger is it then? What's the difference in size between those?
Like hundreds of times larger. It has open-ended categories because the categories are just free-form text. Mm-hmm. But it's really kind of the size, but also the coverage and the variety. The dataset needs to be diverse. It needs to have a lot of stuff in it. If your dataset is narrow, it will hurt the neural network.
When I look back at the last 9-ish years, right, since the ImageNet breakthrough, it seems like year after year, there are new breakthroughs, new capabilities that didn't exist before. Many of them, thanks to you, Ilya, and your collaborators. And I'm kind of curious, how do you from looking back at the last 9 years, and then as you project forward, are there some things that you are particularly excited about that we can't yet do today, but you're hopeful that, maybe become feasible in the next few years? Yeah.
So I'd say that there is a sense in which the deep learning saga is actually a lot older than the past 9 years. It's funny, if you read some of the statements made by Rosenblatt, I think in the 60s. So the Rosenblatt invented the perceptron, which was one of the first neural networks that could learn something interesting on a real computer. It could learn some image classification. And then the Rosenblatt went onto the New York Times and he said, one day a neural network will see and hear and translate and be conscious of itself and be your friend. Something like this. And he was trying to raise money to build increasingly larger computers, and he had academic detractors who didn't like the way funding was misallocated in their mind, and that led to the first major neural network winter. And then I think now these ideas were kind of always there in the background, just that the environment wasn't ready, because you needed both the data and the compute. And then as soon as the data and the compute became ready, you were able to jump on this opportunity and materialize the progress. And I fully expect that progress will continue. I think that we will have far more capable neural networks. I think that, I don't want to be too specific about what I think, like about what exactly may happen, because it's hard to predict those things. But I would say one thing which would be nice is to see our neural networks being even more reliable than they are, being so reliable that you can really trust their output. And when they don't know something, they'll just tell you and maybe ask for clarification. I think that will be quite impactful. I think they will be taking a lot more action than they are right now. I think our neural networks are still quite inert and passive, and they'll be much more useful. Their usefulness will continue to grow. And I mean, for sure, I'm totally certain that we will need some kind of new ideas, even if those new ideas may have the form of looking at things differently from the way we are looking at them right now. And I would argue that a lot of the major progress in deep learning has this form. Well, for example, the most recent progress with unsupervised learning, like what was done? What's different? We just trained larger language models, but they've existed in the past. It just, we realized that language models were the right thing all along. So I think there will be more realizations like this, where things that are right in front of our noses are actually far more powerful and far more capable than we expected. And yeah, and I do expect that the capability of these systems will continue to increase. They will become increasingly more impactful in the world. They will become a much greater topic of conversation. I think that the product, we will see unbelievable, truly unbelievable applications, incredible applications, positive, very, like even transformative applications. I think, we could imagine lots of them with very powerful AI. And eventually, I really do think that we'll be in a world where the AI does the work, and we, the people, enjoy this work, and we use that work to our benefit and enjoyment. And and part of the reason OpenAI is a capped profit company, where after we return our obligations to our investors, we turn back into a non-profit, so that we could help materialize this future vision, where you have this useful AI that's doing all the work, and all the people get to enjoy it.
And that's really beautiful. I like the model you have there, because it essentially, it reflects in some sense, the vision that the benefits of, really capable AI could be unlimited. And it's not great to concentrate an unlimited benefit into a very small group of people, because, that's just not great for the rest of the world. So love the model you have there. One of the things that ties into this, Ilya, is that maybe AI is also becoming more expensive. A lot of people talk about it, that, training models, you want a bigger model that's going to be more capable, but then, you need the resources to train those bigger models. And I'm really curious about your thinking on that. Is it just going to be, the more money, the bigger the model, the more capable, or is it possible that the future is different?
So there is a huge amount of incentive to increase the efficiency of our models and to find ways to do more with less. And this incentive is very strong, and it affects everyone in the field. And I fully expect that in the future, we'll be able to do much more using a fraction of the cost that we do right now. I think that's just going to happen for sure. I think cost of hardware will drop. I think methods will become more efficient in all sorts of ways. There are multiple dimensions of efficiency that our models could utilize that they aren't. At the same time, I also think that it is true that bigger models will always be better. And I think it's just a fact of life. And I expect there should be almost like a kind of a power law of different models doing different things. I think you'll have very powerful models in small numbers that are used for certain tasks. And then you'd have many more smaller models that are still hugely useful, and then you have even more models which are smaller and more specialized. So you'd have this kind of continuum of size, specialization, and it's going to be an ecosystem. It's going to be not unlike how in nature there are animals that occupy any niche. And so I expect that the same thing will happen with compute, that for every level of compute, there will be some optimal way of using it. And people will find that way and create very interesting applications.
Love your vision, Ilya. I think we actually covered a tremendous amount already. I'm really intrigued by everything we covered, but there's one question that's really still on my mind that I'm hoping we can get through, which is, Ilya, you've been behind a lot of the breakthroughs in AI in the last 10 years, even a bit before that. And I'm just kind of curious, what does your day look like? What do you think are some habits and things in your schedule or things you do that help you be creative and productive?
It's hard to give useful blanket advice like this, but maybe two answers consist of protecting my time and just trying really hard. I don't think there is an easy way. You need to just gotta embrace the suffering and push through it, and that's because and push through those walls, and that's where the good stuff is found.
Now, when you say protecting your time, which really resonates, of course, then you get to choose how you fill it in. And I'm kind of curious, if you just look at, let's say, maybe, the last week or the week before, and you're like, protected time, what are you doing? Are you going on walks? Are you reading papers? Are you brainstorming with people? What's going on?
Yeah, I'd say mostly in my case, it would be not necessarily going on works, but lots of solitary work. And yeah, there are people with whom I have very intense research conversations, which are very important. And I think those are the main things I do.
Mm-hmm. I do know that you're also an artist, or aspiring artist, whatever we want to call it, at the same time. Do you think that plays a role at all in boosting your creativity?
I mean, I'm sure it doesn't hurt. So now it's hard to know with these things, obviously, but yeah, I think it can only help.
Well, Ilya, it's so wonderful to have had this chance to chat with you. I mean, it's been way too long since we've had a chance to catch up, and this has been so good to get to know you even better than before. Thank you so much for making the time.
Thank you, Peter. I had a great pleasure being on the podcast.